I'm going to take a little look at this item here. This is a dose rate meter from the Cold War period. It was the Royal Observer Corps were issued with these, and basically it's a type of Geiger counter. It was manufactured by the Plessey company, long gone, along with the same weight as GC, Ferranti, and a lot of other companies. But quite well made, kind of interesting for a kind of army issue. It's a bit fluorescent, but it's quite nicely put together. One of the things that makes it limited use is the scale it actually reads in. It's in centigrays per hour, which is quite a big dose. It does a self-test when you switch it on, which is quite nice, and either passes or fail. This one should pass okay. And it does that because there's a little bit of a radioactive isotope built into the Geiger tube itself, so it has a rate it can do a self-test with, and then it will start measuring. But this is in just normal background, and you see it sees nothing compared to a normal count per second Geiger counter. If we compare it to this Geiger counter, which is a little kit one, which is good. This one's got quite a large kind of pancake Geiger tube on it. You can see it's counting away quite happily, and if I use a check source here, which is basically a gas mantle, so it's a thoriated gas mantle, which sounds incredibly busy. And if I put my strongest check source onto this, it will still measure nothing, which is good. Yeah, to give you an idea of the centigray scale, it's obviously it's a hundredth of a gray, which is a pretty fatal dose when you get into big numbers. So this is definitely a kind of runaway range. If you look at an ordinary dose meter, they're measured in microsieverts per hour, and if my calculations are correct, then it would be 10,000 microsieverts for one centigray. So yeah, right off the scale by a big factor. So it's definitely a range you're not normally playing with. So it's held together just by 4 screws in the corners here, and if I remove these we can take it apart. It is quite waterproof, which is quite clever. The battery compartment is separate from the container and also has a seal on it, which is quite a clever construction, particularly for something that's used out in the field basically. Inside we've got this little circuit board. And if we zoom in a little closer, we have the Geiger tube here. It's cased in a kind of lead casing, so it's really designed just to pick up gamma radiation. We have the supply from the batteries coming in here. There's only a couple of chips on it. This one is basically a dual 4-bit binary counter, and the one on the other side is a proprietary Plessey one, which I can't find any information on. Has a crystal on it, so whether there's any kind of processing, I'm not too sure. I think basically it's the LCD driver for the 7-segment LCD display. This is a high voltage transformer, and there's a multiplier circuit here as well. There's a strange LED here which looks to me as though it's really just indicating the voltage. There's also a voltage supply out of the high voltage circuit, and this is really amplification for the pulses from here. It's all driven by just 4.5 volts and designed to actually run for about 400 hours on these batteries. Single-sided printed circuit board. Let's say there's the Plessey proprietary chip on this side. Now we can see a rather interesting thing here. This resistor going onto the Geiger tube here is actually on a little coil here on the circuit board. gives it a bit of movement. I don't think that's an inductor for any purpose. I think it's mechanical. I think it's just if there's any shock or movement on the tube, it's not going to crack the connection onto the printed circuit board. So let's see, could it be used for anything? Let's try it with a little dose of X-rays.